Welcome back. We are in the last subtopic of chapter thermochemistry, Born-Haber cycle. So, learning objective A, basically we already discussed in the video number 8. Okay. Define the lattice energy. As we know, lattice energy can be have two types. One is enthalpy formation, and which is always negative value, while enthalpy of dissociation and our lattice energy always is positive value. Okay, then next we also learn about the electron affinity in the video 8 as well. So for this one, electron affinity, generally the first electron affinity always is negative value, while second and onwards of the electron affinity always will be the positive value. Then learning objective B is the one we have to explain the factor will affecting the magnitude of the lattice energy. This is the two factor, ionic charges or the radius of the ions. Next is the main content of this video, construct the Born-Haber cycle. So you will notice later when you want to construct Born-Haber cycle, there are two types of Born-Haber cycle. One we call is energy cycle diagram. Another one we know it as energy level diagram. So after we construct the Born-Haber cycle, basically sometimes they will ask us to calculate the missing enthalpy for the Born-Haber cycle. Let's start with learning objective B, factors that will affecting the lattice energy, which we have two factors. The first one is ionic charge, and then the second one is the ionic radius. Okay, so when we look at the first factor, ionic charge, based on here, the greater the ionic charge, the higher the magnitude of the lattice energy. So for example, we have lithium fluoride with the magnesium oxide. So as we know, lithium is lithium plus F negative, Mg2 plus with O2 negative. So because the charge is higher, so when we want to do the explanation, we will mention attraction force between Mg2 plus and O2 negative is stronger than lithium plus and fluoride ion. Okay, so when the attraction is stronger, so therefore more energy required to dissociate them. Okay, so if more energy required to dissociate, so the magnitude of the lattice energy magnitude is greater. So another one is the ionic radius. So for the ionic radius is inversely proportional to the size. The lattice energy is inversely proportional to the size. However, we will notice that the explanation is similar with the factor of the ionic charge. So for example, NaCl, we will have Na plus Cl negative, Na plus Br negative. So in this case, we will notice that their charge are similar. So now what's the difference between here? Is one is Cl negative and then another one is Br negative. So as we know, Br negative is at the bottom of the group 17. So the size is greater, and then this one, the size is smaller. So again, we are going to use the term attraction force between Na plus and Cl negative is stronger. The smaller the size, so easier to attract, will be more So it's stronger than Na plus and Br negative. So again, more energy required to overcome the attraction between Na plus and Cl negative. So magnitude of the lattice energy for Na plus and Cl negative is higher. So from here we notice that lattice energy higher, but the size is smaller. So that's why we say it is inversely proportional. So we continue with tutorial question number 4. By combining the idea in front there, so we have the idea that the lattice energy is directly proportional to the ionic charge, okay, but inversely proportional to the ionic radii. So if now this question asks us to determine the highest lattice energy, so we're going to Na plus Br negative, K plus F negative, and K plus I negative, Na plus F negative. Okay, so when we look at here, so basically all are positive charge and negative one charge. So that's why the factor that we are going to consider in this question is not ionic charge, but we need to consider the ionic radii. So as we know, between the Na plus and the K plus, Na plus have smaller size. So maybe we can more consider on Na plus. But then in between the negative charge, F negative is the smaller size. Then from here we know that the answer basically will be the donkey NaF. Now let's proceed to tutorial question 13C. Compare and explain the differences of the lattice energy between magnesium fluoride and NaF. So as usual, we are going to write down the ion for magnesium fluoride Mg2 plus with F negative, and then Na plus with F negative. So from here now, we can notice that the difference between these two ionic compound, magnesium fluoride and sodium fluoride, is the magnesium 2 plus and also Na plus. So when we look at here, we notice that they are different in terms of ionic charge. They also different in terms of ionic radius. So when we have both factors are affecting, so we will focus on the priority we'll give to the ionic charge. So for the part C1, we will going to say, because Mg2 plus has greater ionic charge, so we will say that attraction force between Mg2 plus and F negative is stronger than Na plus and F negative due to, so because we need to explain, we need to give the reason, due to Mg2 plus show greater ionic charge compared to Na plus. So next we will look at the calcium fluoride. So we have Ca2 plus and F negative. So this time when we compare in between these two ion, so Mg2 plus, so the Mg2 plus has and Ca2 plus are different, since both of them are having same ionic charge. So means that we are going to compare with the ionic radius. So for C2, the factor that we consider is ionic radius. So calcium is at the bottom of magnesium. So again, we will repeat the terms. Attraction force between Mg2 plus and F negative is stronger than calcium 2 plus and F negative due to Mg2 plus show smaller ionic radii compared to Ca2 plus. Okay, now we go to the main content for this video, Born-Haber cycle. Basically, this Born-Haber cycle is developed by the Max Born and also Fritz-Haber. So that's why we use both of their name, Born and Haber. So in this Born-Haber cycle, we are going to relate the enthalpy of formation for an ionic compound and then relate with the atomization, ionization energy, electron affinities, and also lattice energy. So basically, these are the 5 types of enthalpy will be involved in the Born-Haber cycle. However, you will notice most of the time in the question, they will always ask us to determine the lattice energy. However, it is also possible to ask us to determine the enthalpy of formation, atomization, ionization, or electron affinity. That means one of the enthalpy in this list. So beside draw the energy level diagram, beside draw the energy cycle, sometimes we also will be asked to draw energy level diagram. So when the question asks us to draw the energy level diagram, then we have to keep in mind that if the value given is positive, means that we absorb the heat, the system absorb the heat. So you will draw the arrow upwards. However, the other way around, if it is negative, means that release energy, so the arrow should be downwards. So again, before we continue, you might try to remember this. Formation always equal to atomization for cation, anion, IE for cation, and then here should be the EA of the anion and lattice energy. Tutorial question 13. Based on the following data, you are given the enthalpy of atomization for magnesium, fluorine, ionization energy for the magnesium, electron affinity for the fluorine, and then formation of the magnesium fluoride. So again, need to remind you that the importance of knowing the definition of different types of enthalpy. Again and again, you will notice that sometimes quite often the question will give us the name of the enthalpy without the thermochemical equation. So you are the one who going to construct or write down the thermochemical equation. So before we can construct the Born-Haber cycle, so we need to write down the enthalpy, the thermochemical equation. So let's first start with the enthalpy of the atomization for magnesium. So 1 mole of gaseous ion formed from its element. So magnesium is metal which is always in the solid state. 1 mole of gaseous ion, so formed from its element, so will be from solid to gas. So this one, the enthalpy is equal to positive 148. So we'd like to remind that because of this one is changed from solid to gas, in this case, the enthalpy of the magnesium also can be considered as enthalpy of the sublimation of magnesium. Normally, this only will be applied for the metals only. That means if the metal, the thermochemical equation for the enthalpy of sublimation of metal will be similar with enthalpy of the atomization. Again, only apply on the to the metal only. Okay, so next, the thermochemical equation that we're going to write is enthalpy of the formation of fluorine. So we know that fluorine is element in group 17. So always exists in diatomic molecule. Fluorine is gas, and then going to form one more of gaseous atom. So this chemical equation is not balanced, so we have to put 1 over 2 in front of fluorine gas because we want to make sure there is one more of gaseous atom is formed. So the enthalpy is positive 159. Next, we're going to continue with the ionization energy. Energy required to remove one more of electron from its gaseous atom. So that's mean from gaseous atom, after remove one more of electron, you will get magnesium ion gas plus electron. So this delta H equal to positive 738. While second ionization energy is magnesium ion, and then remove one more electron, become Mg2 plus gas plus electron. Second one is positive 1450 kilojoule per mole. Okay, so we will continue the second electron affinity and enthalpy of formation in the next slide. Okay, let's continue with the electron affinity of the fluorine. Electron affinity of the fluorine is means gaseous fluorine atom gain one more of electron, and then will produce a gaseous ion, and then the energy is negative 328. Next one is enthalpy of formation for the magnesium fluoride. When one more of magnesium fluoride is the ionic compound, so in the solid form from its element. So the element for the magnesium fluoride is magnesium solid and also fluorine gas. So the enthalpy for this one is negative 1123. Okay, question number 13a is asked us to construct the Born-Haber cycle. So before we want to construct the Born-Haber cycle, maybe you can write down the sequence of the type of type of enthalpy that involved in the Born-Haber cycle. As we know, formation always equal to atomization, and then involve both cation and anion, followed by the ionization energy, electron affinity, and lastly is the lattice energy. Okay, so we just simplify like this. So we start from the formation. So from here we notice that magnesium solid magnesium react with fluorine gas will produce magnesium fluoride. So this is the formation. So we involve this one, we put the negative 1123 over here. Okay, next we are going to do the atomization, means that magnesium solid will become magnesium gas. So this one is fulfill this first equation, which we will label here positive 148. Then, because we will do it one by one, after all the metal, then we continue with the non-metal. So for metal, it will involve the ionization energy, will produce Mg plus gas, which is positive 734, and then followed by magnesium 2 plus gas. The enthalpy is positive 1450. So we already settled for atomization and ionization energy. Then we move to the non-metal. So for non-metal, fluorine here, 1 mole of fluorine will produce 2 more of gaseous fluorine atom. Okay, so therefore, but based on this equation, only will produce 1 more gaseous atom. But here we need to produce 2 more of gaseous atom. Therefore, the enthalpy of atomization need to multiply by 2. Okay, then consider settle for the atomization of nonmetal. Next one, we continue with the electron affinity. So 1 mole of gaseous atom will going to produce 1 mole of gaseous ion. So we have 2 gaseous atom, means that it will produce 2 more of gaseous ion as well. So that's why for this one, we are going to multiply with 2 as well. So we also already settled for the electron affinity, and the last one is the lattice energy. So as we always remember, if lattice energy means that it's referred to lattice formation, which is mean when 1 mole of solid ionic compound is formed from its gaseous ion. So the gaseous ion is over here. So gaseous ion is the reactant and then going to form the magnesium fluoride, which this is the lattice energy. Then don't forget that we have to put the positive sign over here. Then now next we are going to calculate the enthalpy of the lattice energy. So as we know here, the starting point is magnesium and also fluorine gas. Okay, so this is the starting point. And the destination is here, magnesium fluoride. Okay, so this is the destination. So basically what you memorize over here, you try to look at it. Only one step, which is referred to the formation. So equal to atomization. This one is formation, atomization, first IE, second IE, okay, and then atomization, electron affinity, and lastly is the lattice energy. So basically this formula that you memorize is follow the Hess's law as well. So since the question B is asked us to determine the lattice energy, so you can just put in the value, -1123 is the formation, equal to the atomization 148, and then plus 159 times 2, and then plus positive 738, and then plus positive 1450 ionization energy, and then plus the electron affinity -328 times 2, and then plus the lattice energy. So we only have one unknown in the formula, so end up we are able to determine the value of the lattice energy, which will be in the unit of kilojoule per mole. Okay, after having a question about the Born-Haber cycle, then now if we look at question number 14, it will ask us to construct the Born-Haber cycle using the energy level diagram for the lithium oxide. Okay, so lithium is lithium plus, oxide is O2 negative. So basically the formula is Li2O. And then we need to calculate the enthalpy of the formation. So from here we think that it is possible because in the Born-Haber cycle we will have the formula formation equal to atomization, ionization energy, electron affinity, and also lattice energy. Okay, so question 13 and question 14 is a bit different. Question 13, they give us the type of enthalpy without the thermochemical equation. While for the question 14, they give us the thermochemical equation without the type of the enthalpy. So again, it is very important to understand the definition of the type of enthalpy. So before we can construct the energy level diagram, so it will be better we identify first the type of the enthalpy. So this is lithium from the solid to the gaseous atom. So we can consider this is enthalpy of atomization. Gaseous atom remove one more of electron and then produce gaseous ion. So this is ionization energy. Gaseous atom from its element. So this is atomization. So oxygen gases gain one more of electron, become O negative, become electron affinity. So this is the first electron to be gained. So we refer to first EA. So when become 2 negative means that they already received the second electron. So and then here we notice that one more of solid ionic compound is formed from its gaseous ion. So it's referred to lattice energy. Okay, so maybe you will say that means why we have not seen any electron in here. Okay, so yes, because this is given in the question, so if they didn't show the electron, then should be no problem because they want you to able to identify. But if you are the one who write the thermochemical equation, so you have to make sure that this is the oxygen plus O plus gain electron. So this one, sorry, is O negative and then gain electron as well. Okay. So in simple words to say, if the information given in the question, it may be not complete as what we write down. So, but when it is your answer, so you have to write as complete as possible. So after identify all these, then we roughly check back here. Formation equal to atomization, ionization energy, electron affinity, and lattice energy. So basically, atomization is given in the question, i.e. ionization energy, electron affinity, and also lattice energy are here. So means that we are the one who going to find out the enthalpy of the formation. Okay, before we continue, draw the energy level diagram. Let's label again. So this is referred to atomization, and then this is ionization energy, atomization, first electron affinity, second electron affinity, and last one is the lattice energy. So the question is asked us to draw the energy level diagram. So we may start with drawing a line which is at the left hand side, and then we label energy with the unit of kilojoule. Then don't forget we always have to start from 0, which basically is represent the element, because element occurs naturally and always no need to absorb or release energy, so the enthalpy is equal to 0. So we start with the what we know about the formula for the so-called like formula of the Born-Haber cycle. Basically, it will involve enthalpy of formation equal to atomization plus IE plus EA, and lastly is the lattice energy. So here we want to form the lithium oxide, and then the element for the lithium oxide will be lithium solid and oxygen gas. Okay, so as we know, formation is heat release, always negative value. So that's why we have to show the arrow going down, and then we draw one line. Lithium, because lithium plus O2 negative, interchange the charge. So we will get the formula lithium Li2O, and then this one is the solid. Okay, so as we know, this is enthalpy of the formation, and we have no idea yet. Okay, we need to draw the energy level diagram to determine the enthalpy of the formation. Okay, before we proceed, then you will notice that this equation is not balanced yet. Okay, here only have 1 mole of lithium, but the lithium oxide have 2 mole of lithium. So what we're going to do, we balance this equation with 2 mole of lithium, and then for the oxygen is 1/2. Okay, maybe I use plus over here, and then 1/2 mole of oxygen gas. Okay, so then now we already settled for the formation. Next one, we goes to the atomization. So we do the atomization for the lithium first. So from the lithium, the will become 2 mole of lithium gas. Since we do one by one, oxygen is remain unchanged. So we just write down first 0.5 mole of oxygen gas. Since here we notice the difference is over here. 1 mole of gaseous ion is formed from its element. But now here we form 2 mole of gaseous ion. So we're going to use this formula 159.4. Okay, so 159.4 times 2. Okay, so next, after the atomization for the lithium, then we can proceed with the atomization for the oxygen gas. So this time, 2 mole of gases lithium maintain. Oxygen gas will become 1 mole of gaseous oxygen atom. So we already settled for the atomization for the lithium, and then the next one is the atomization for the oxygen, which is positive 249.2. Okay, so we can label over here. This is positive 249.2. Okay, after done for the atomization energy, next one is the first ionization energy. Okay, so we go up again because we see this ionization energy is positive value. Okay, so after this we will get a 2 lithium gaseous ion plus O gaseous atom. So again we have a 2 mole of lithium gaseous atom. So this value positive 520 need to multiply with 2. So after settle for the ionization energy, next we going to the electron affinity. So when we look at the electron affinity, this one is the negative value. So means that it will be going down to produce. Okay, so since it is a bit so we write down here positive 520 times 2. So maintain over here. Then this one now here is like this. 2 mole of gases lithium ion we maintain over here because nothing happened to them. 2 mole of lithium gaseous ion. And then next one, because of the oxygen will get 1 mole of electron, so will be plus O negative gas. And then for this one, the label is negative 141.1. So after settle for the first ionization energy, then we will proceed to the second electron affinity. So second electron affinity is positive sign, so that's why you have to write down going up again. So once going up here, the 2 lithium gaseous ions still maintain the same, but the gaseous oxygen ion from O negative will become O2 negative gas. So here the enthalpy is positive 798. So this one we delete first. Okay, then the next one is lattice energy. So we want to mention about the lattice energy. So we will notice over here, maybe I use another color. So lattice energy is gaseous ion to the solid ionic compound. So gaseous ion is over here, ionic compound is at the bottom here. So basically again we will use the arrow to show the negative sign over here. So this one, the energy is negative 2862.8. Maybe I need to erase this one. So again, from here, it will be going down. And then the value over here is negative 2862.8. Okay, after that, we move the energy level diagram that we draw in the previous slide into here, which is more proper. So you will notice that we need to, from this energy level diagram, again, we also need to identify where is the starting point. So I think for this one, we miss out the 0 over here. Please label it. So from here, we will notice that the arrow is come out from the element. So this one will be the starting point. So maybe you can label as here, this is the starting point. And then the destination is over here, okay, because two arrow is pointed at in here, okay. This one is two arrow pointed out. So okay, two arrow is pointed out from here, and then two arrow is pointed into here, okay. So that's why we know that this is the destination, so called. Okay, so then from here, this one is enthalpy of the formation, which is only involve one step. So, and then how to get the enthalpy of formation? If we cannot one step go down here, then we have to go through enthalpy of delta H1, 2, 3, 4, 5, and 6. So that's why we total up enthalpy of the 1, 2, 3, 4, 5, and 6 over here, and then we substitute the value in, then press the calculator. You will notice that the enthalpy of the formation is negative 597.9 kilojoule per mole. So when we look at over here, the arrow is showing going down, okay, it's downwards. So it is logic that we will get the negative value. So here also negative value means that our answer is correct. So basically we already finished discuss all the tutorial questions for the chapter thermochemistry. Okay, so now let's finish this video with the summary of the Born-Haber cycle. So as a reminder in the beginning of the video, we have to remember this formula. Formation always equal to atomization plus ionization energy, electron affinity, and also lattice energy. Okay, and then the sequence must be followed as this. You cannot mix up the sequence, or no, later you will find that it is very difficult for you to draw a complete Born-Haber cycle. Okay, next, beside from the knowing the type of enthalpy, maybe we also can focus on the reactants about. So reactant for the formation always is start with the element, and then for the atomization always will be end with the gaseous atom. For the electron ionization energy and electron affinity, always you will end up with the gaseous ion, and then the gaseous ion will end up with the solid ionic compound. So basically, these are the type of enthalpy and also the physical state for the substance or the particles that will be appear in the Born-Haber cycle.